Shaders. Shaders, and more shaders. Everyone talks about shaders. There are plenty of tutorials, showcases, and explanations of what shaders are and what they can do. But moving away from what's told with shaders, let's mention what isn't. In this video, I will cover 10 shader tips and tricks no one teaches, but is crucial to have in your arsenal. And there is one tip that ties everything together. A tip that without, the other ones crumble. But for that one to make sense, let's first start off with what is a shader. A shader is a small program that runs on a per item basis. This item can be substituted with vertex, pixel, etc. So for each item that the program runs, it will forward it to the next step in the graphics pipeline. If you need more info about the graphics pipeline itself, I have a video on that, go check it out. Let's begin with the tips and tricks. Tip 1. Branchless Programming. CPUs are great machines that can literally remember and even guess what your next step is going to be. GPUs, not so much. Their biggest pros aren't the core power itself, but it's the amount of cores the GPU has. So it's a very efficient way of running things asynchronously. Therefore, avoid branching at all costs. Instead of having ifs in your code, multiply by a bool or use a lerp if the A and B are easy to compute. Precompute values and store them in a structure, like a texture. For example, a lookup texture, LUT. The last tip is avoid discarding. Even though discarding is a good thing because you don't run the pixel shader, discarding can actually harm your performance because if you do it too often on a per pixel basis, it might hurt the branching. Instead, try to do it every other or every third pixel. Tip 2. Bitflags. So you might need bools on the GPU for certain conditions, but bools can only hold true or false value while still being a 16-byte aligned variable on the GPU. Therefore, if you need flags on the GPU, send up a int instead and bit shift. Inside of a int, you can store 32 flags instead of a bool where you can only store 1. Use the bitwise operator AND to check if the bit is on. Use the bitwise operator OR to check if the bit is off. Tip 3. Includes. Using includes in shaders is usually fine. But what if you get conflicts? Or if you want to include something both in the shaders but also in the C++ files. Therefore, you should follow these guidelines. C-style pragma once in all your HLSLI files. Cover your whole file in a if not define check. Inside of that if not define check, define what you're actually checking against. This will ensure that your file can be included in multiple places without interfering with each other. It's exactly what pragma once is doing in C++. You can also include .h files in HLSL or HLSLI files. Just remember to also do the C-style pragma once and not rely on the pragma once macro. You can also define __C++ if you want certain variables and stuff in there to only be defined in the C++ files and not in the included .HLSLI or HLSL files. For example, you can have a function in the header file that does something with a vector4, but if vector4 isn't a thing, which it isn't in HLSL, you can use __C++ and then in the else you can specify what it's called in the shader. So in HLSL, a vector3 is a float3 instead. Tip 4. Precompute values. It might seem that setting up as little as possible to the GPU is the most optimized. But you gotta remember that a shader is something that runs on a per item basis. So calculating the inverse of a matrix per fragment isn't necessarily the most optimized either. Therefore, you should pre-compute values, like for example the view projection, which can be calculated on the CPU and sent up to the GPU one time. Tip 5. Understanding maths. Maths are used everywhere in computer graphics, and shaders are no exception. Therefore, it's important to learn bits of it, whether you like it or not. A great example of an optimization we can do with just a little bit of math knowledge is reducing the amount of time we inverse matrices. Vector 4 times the inverse of a matrix is the same as matrix times the vector. if the matrix inverse is equal to its transpose, which is the case with pure rotation and translation matrices. So you can skip the inverse there if you move the matrix to the left-hand side of the equation. Tip 6. Pixel derivatives. How do GPUs achieve smooth effects like anti-aliasing and texture filtering with things like pixel derivatives? This can be used, for example, anti-aliasing and anisotropic effects, filter effects, blurring, and getting the texel density of an object. And if you're doing a full screen effect with a compute shader and pixel derivatives aren't something implemented in that shader model, read this guy by Janusz Torański. That enables you to make smooth texture sampling and not relying on loading pixel per pixel. Tip 7. Packing data. GPU data is automatically 16-byte aligned, so sending up an int is actually not just sending up 4 bytes, it's actually sending up 16 bytes with 12 of them being padding. Therefore, it's extremely important to know how you structure your data when you send it up to the GPU. For example, can you spot the issue in this structure? So we have a float 2, a float 4, a float 3, and then a bool array with 4 indices in. Well, we'll first have the float 2, then we will have padding of 8 bytes, then we have the float 4, which is fine, and then we have the float 3. After the float 3, there will actually be another 1 byte of padding before the bool array happens. And if we look at the bool array, we might think that it's fine. It's 4 bools, which should be 4 bytes, right? Well, that's wrong. When we do an array structure like this, it's going to do bool and then padding of 3 bytes. Then bool, and then a padding of 3 bytes again, then bool, a padding of 3 bytes, and then bool, a padding of 3 bytes. So instead of having 4 bytes, which we thought it was, instead it will be 16 bytes. That's 3 times the amount we thought it was. So make sure to pack your data correctly, or add your own padding so that you know what is happening. You can also use declspec, align 16 or align as 16 to make sure that the CPU structure is always 16 byte aligned. Tip 8. Acquiring worldpos from depth. When making shader effects, you will often require the world position of the pixel. But if you have a forward renderer or a deferred renderer without the world position, which you should have, it can be hard to get the world position. Well, you can get the world position from the depth in various ways. svposition.z is your depth in NDC space if you render, for example, an object like a model. Lerping that with the near and the far plane will get you the depth in the frustum. Now we will act the GPU pipeline to get the world pulse from the depth. We first get the clip space coordinate, which we get by using the screen UV, which is in 0 to 1 space. We multiply it by 2 and we subtract 1, which will get us -1 to 1 space. And then we use the depth as the z parameter. We multiply the clip space by the inverse of the projection, which will take us into view space. We then take the result of that and multiply by the inverse of the view space, which will get us in world space. You can also get the depth from worldpos. So if you have the world position and you want to retrieve the depth, you take the world position coordinate, multiply that by the view matrix, and multiply that with the projection matrix. That will give you the position in the clip pos. We then do the perspective divide. That will give us the depth, which is 0 to 1. The reason we can't just sample from the depth buffer because the depth is bound as the output, so we cannot use it as input. Tip 9. Shader compiling. Have you ever tried to search for a function in your shader and didn't find it? Or tried compiling your applications but you couldn't because of your shaders? Well, enter the shader compiler and the shader model compatibility. Make sure your shader level is set to the correct one. Also, be sure to compile your shader with debug flags if you want the correct information in programs like RenderDoc, Nsight, and Pix. Lastly, you can optimize your shaders by compiling correctly. Use hints or compiler directions with unroll, loop, and branch semantics before for loops. Tip 10. Compute shader cluster size. Knowing what cluster size to run on your compute shader is hard. But remember that your GPU works in clusters of 64, so dispatching inefficiently wastes computational power. Therefore, dispatch your shaders with values that are multiple of 64 to make the most out of your compute shader. Usually those are the guidelines, and you can experiment from there. All these tips are great, but they are nothing without having something that can actually show you and analyze the performance gains. Run Insight on your projects and have a look at these stats: texture, ROPS, L2, VRAM and L2 hit rate. There's a great guide by NVIDIA that shows you how you can use Insight to its fullest potential. I will also link that in the description. Shaders are amazing programs that makes the pipeline both optimal and comfortable, but always have these tips in mind when you do shader programming. Whilst they're not necessary, they're really good to have in the back of your head when you try to do some shader optimizations. But a lot of these tricks and shader programming in general wouldn't be possible for me if I didn't learn maths the right way. If you just need a nudge in learning maths or want to learn from my mistakes, so watch this next video which talks about how you can learn maths in a better way.